let's start talking about entropy. Good? Entropy. A chemical system will tend to achieve the lowest possible energy. But that idea that the physical and chemical systems have the lowest possible energy has a corollary. And that corollary is the law of disorder. The law of disorder states that things move spontaneously in the direction of maximum chaos or maximum disorder. It just means that it goes with, okay? So the whole idea is that the chemical system will achieve the lowest possible energy, but at the same time that it's achieving that, we have this law of disorder that goes hand in hand. So even though it wants the lowest possible energy, things are moving towards the greatest possible disorder, maximum amount of chaos. And that is what entropy is. The measure of the amount of disorder in a system is the entropy of that system. So, the law of disorder also applies at the level of atoms and molecules. And we can apply the following concepts to that. So, now what this is actually saying, folks, the entropy of a gas is greater than the entropy of a liquid or a solid. Stop and think about the kinetic theory, okay, the kinetic molecular theory that we talked about earlier. Where is there going to be more disorder? In which state, solid, liquid, or gas? Gas, they're going to be moving faster. They're going to have less order. So there is more disorder with the gas. You would think that the next one would be a liquid and the last one would be a solid, because solids are pretty well ordered, aren't they? Well, that it tends to be the case. So the entropy of a gas is greater than that of a liquid or a solid. The entropy of a liquid is greater than that of a solid. And in this reaction right here, if I look at it, I can see that I have the decomposition of calcium carbonate into calcium oxide and carbon dioxide gas. Now, you'll learn a few things here, folks, but I can see that I have a solid that is decomposing to a solid and a gas. So where is there going to be more disorder, on the reactant side or the product side? The products definitely are showing us more disorder. Okay? A couple of things. We can see it's going from a nice solid, one substance, into a gas on the other side. That is one hint that we're increasing the entropy. Another hint would be that I have one reactant, and it goes into two products. So that's going to be another one of the situations that we'll talk about here coming up. This is what I was talking about just a second ago when we had the one product, the one reactant turned into two products. Okay? Here we go. This one is a little bit more. Okay? I have sodium bicarbonate. Sodium bicarbonate is decomposing into sodium carbonate, water, and hydrogen gas, carbon dioxide gas. So if I look on my reactant side right here, on my reactant side, I have one reactant. When I undergo this chemical reaction and break it down, I have three products. What do you think is more disordered? One reactant or three products? Three products, okay? Because it says the entropy increases when a substance is divided into parts. Okay? Therefore, increases in chemical reactions in which the total number of product molecules is greater than the reactant molecules will give us more entropy. A third part, entropy increases with a temperature increase because the motion of the molecules become more chaotic. Molecules are more disordered at higher temperatures than they are at lower temperatures. We talked about that just a second ago, that those molecules are moving greater at higher temperatures than they are at lower temperatures. Thus, increasing temperature increases the amount of disorder or chaos and will therefore increase the amount of entropy. So, let's look at some actual calculations. Now, I just gave you a data table that is going to be very important when we're discussing thermodynamics, which is what we're getting into. This is thermodynamic quantities for selected substances at 298.15 Kelvin, which is equivalent to 25 degrees Celsius. So on that data table, it has values for certain things. We're going to go over some entropy calculations, and I think that you'll find these pretty easy if you can add, subtract, multiply. Okay, I think you should find these pretty easy. The symbol for entropy is the letter S, and the units for entropy are joules per Kelvin. So I want you to find the entropy column on your chart. Find the entropy column on your chart and point to it so I can see that you know where it's at. Point to it, point to it. Entropy. Did everybody find this? There should be two of them because this is really a split chart. So there should be two of them. The standard entropy of a substance in its stable state at 25 degrees Celsius, 1 atmosphere of pressure, is designated by an S with a exponent of, sort of like an exponent of O. So that little S with the superscript O right there is the standard entropy. That's what we call it. The standard entropy, and that is at STP because, or it's at, well, it's not at STP, it's at 25 degrees Celsius, not 0. So it's at 25 degrees Celsius and 1 atmosphere of pressure. So that is our standard entropy. Now we're going to do an example here. I'm going to give you a second to copy down this example. We're going to start off, folks, we're going to start off real nice and easy. It says calculate the standard entropy change, delta S. Remember that delta, the Greek delta, just means change. So this is the change in the standard entropy that occurs when 1 mole of water vapor at 25 degrees Celsius is condensed to 1 mole of water at the same temperature. So what we have is we have water changing states. It's going from the liquid state to the, it's going from the gas state to the liquid state. All right? So, as I'm drawing an equation for this, I am going to have water in the gaseous state producing water in the liquid state. Now, where would this occur? You've got a nice glass of ice water on a real hot summer's day. Okay? A real nice glass of ice water. You have it sitting out in the heat. The coolness of that glass will take water vapor from the air and condense it, and thus you will have what we call a sweaty glass. It'll have water on the outside of that glass. Okay? Now, based on our 3 things that we just learned about how entropy increases, okay, we can predict that how the entropy will go here. All right? I look at this and I say, okay, I have 1 reactant, I have 1 product. So that doesn't give me any hints, does it? But I have a gas going to a liquid. So am I increasing my entropy? Am I increasing entropy? No, I am decreasing. I'm getting more ordered, not more disordered, correct? So remember that. I can predict right here that I am having a decrease in entropy. That is my prediction. Now, how am I going to be certain? Well, here is the equation that we will use to calculate our change in entropy. Delta S super O is equal to S super O of the products minus S super O of the reactants. So the standard entropy of the products minus the standard entropy of the reactants. Now, look back at that equation that I just gave you. What are the products? The products. What is the product of that equation? It is only one. It is water in the liquid state, right? Because where are the products at? Right of the arrow, correct? So what is the value for water in a liquid state? What I want you to do is I want you to find that on your chart. And I believe they're pretty much in alphabetical order. So find water in the liquid state. As I look through and look through, I would say it's on here, but I haven't. Second page, right column. Yeah, it's under oxygen. It's under oxygen. H2O liquid. What is the standard entropy H2O liquid? 69.91. Now stay right there. Stay right there, because what were our reactants in this? H2O gas, right? So what is H2O gas? 188.83, correct? So in order to determine our change, we are going to take those values. Now, my values right here are different than that, but are they somewhat the same? They're ballpark. I'm going to go ahead and change them. Now, if you look at this, okay, if you look at this here, folks, when we go through and see that the 118.92, that's a negative number, isn't it? Okay, so we have a negative number, meaning that the reactants were much more disordered than the products. So we are losing entropy, aren't we? We are gaining disorder. Now here is problem number 2. What is the standard change in entropy for the following reaction when all reactants and products are in the specified states? I have nitrogen monoxide with oxygen to yield 2 molecules of nitrogen dioxide. So what we have here, make sure you write down this equation, okay? Make sure you write down this equation, because I don't have the equation on my next slide. Now the thing about this, folks, is the coefficients out front. Notice that we have them. Did we have them on last problem? No, we did not. Based on our 3 principles that we discussed earlier about entropy, I have all 3 of these are in the gaseous stage. So does that tell me anything? No. But I have two reactants going to one product. What does that tell me? Am I becoming more ordered or am I becoming more disordered? I'm becoming more ordered because I'm going from 2 to 1. 2 products to 1 reactant. Now, what we're going to see, people, is that we're going to take the change in the standard entropy. Once again, it's just going to be the standard entropy of the products minus the standard entropy of the reactants. Standard entropy of the products, standard entropy of the reactants. Now, what is the standard entropy of my product, NO2? What is that? 240.45. But when I look at my reaction, how many of those do I have? 2 of them. So I've got to multiply that by 2. Okay? What is the standard entropy of NO, nitrogen monoxide? 210.62. How many of those are there? 2. So I have to multiply that by 2. And I can find oxygen, which is oxygen diatomic as a gas is 205.0. How many oxygens are there, though? There's only 1, so do I need to multiply it? No. So my next part should look like this. And when I multiply the ones I have 2 together, I should have 480.9 joules per Kelvin minus parentheses 421.24 plus 205. Now, why did I add these together here? Because they are both reactants, aren't they? They are both reactants. So you have to add the values together of all of the reactants. If you would have multiple products, would you add all their values together? Yes. Do coefficients in front of the numbers matter? Yes. So what does that tell you? You need to have a balanced chemical equation. So when I go ahead and do my math, I'm going to have 480.9, and I'm going to subtract from that 626.24, and I'm going to come up with a value of negative 145.34 joules per Kelvin. So am I getting more ordered? Yes, I'm losing entropy. Well, this is just for, these are values per mole, okay? These are values per mole. But do you understand the math of it? Okay? What do you think? We got a thumbs up? Remington? Okay. I'm seeing thumbs up all around. Okay. You've got 5 minutes. You've got a WebAssign that is active. Okay? You got 5 minutes. You got an active WebAssign. Why don't you check it out?